So before I start today's lecture I am going to discuss about what is topology. Let me explain that why instead of continuing with the discussion of functional analysis, I have decided to switch to topology. The reason is very simple. First of all, I already explained that what was the need of functional analysis, because modern day nonlinear control we can clearly identify two different genera of theory. One is generated from the analysis ideas of differential geometry, based on differential geometry, and the another contribution is purely based on functional analysis. Now, uh, and also I have mentioned that it is not totally disjoint set, like there is nothing exist in that overlapping region. It is not true. There exists a large intersection area between functional analysis and your differential geometry. However, before we go to the differential geometry, I started functional analysis because it is somewhat easier for us to grasp, because we are already acquainted with function, the notion of function, mapping, all this. Then we started discussion. However, after a certain point, when I realized that after that I can carefully avoid taking the name of topology in my discussion if I follow the book of Arvind Kreshchik, An Introduction to Functional Analysis. I can, in that book, he has discussed the topological things, topological ideas, without taking the name of the topology. So, what I decided that in the later stage, as I have also, it will be required to cover up manifold, Lie algebra, all these things. So, the idea of manifold, Lie algebra, all these are dependent on topology. So instead of carefully avoiding it and discussing it concept without taking it name, what is wrong if I take the name of that topology? And instead of hitting the bush, go directly to the discussion of topology. So, in the branch of topology, we can utilize the concept of abstract concepts of algebra, or another way we can proceed is from the idea of geometry, and there exists Euclidean and non-Euclidean topology, but I would like to discuss more on Euclidean topology because that will be more useful for our purpose. So, what is topology? Even you can see that your power system, or sorry, power electronics friends will also use this term. We are having two circuits having same topology. So basically topology is a branch of mathematics for which means other branch of mathematicians usually like mock the topologist by saying that they are the people who cannot distinguish between a coffee mug and a donut. Why this coffee mug and donut is very important? See that by means of, if you do not tear, do not break, do not do any kind of, only you just try to change the shape, then by means of that shape transformation, if you just means instead of how much coffee you can pour here in this coffee mug, that is the means how much you will dip it, that depend on your choice. Now if you decide that no, let me fill the coffee mug, and then let me show you a step by step picture. So here you can see that how a coffee mug can be transformed to donut, and donut can be transformed back to coffee mug, vice versa. In the literature of topology, we call it, they are homeomorphic to each other. We will discuss it, what is homeomorphism. Now, broadly speaking, topology is that means like the particular branch of mathematics that is not concerned with the shape, rather they are mainly concerned how two elements are connected, or like means even if you deform, what shape it will take, right? As all of us are from electrical engineering background, let us try to understand it by means of, or by taking an example of electrical circuit. Suppose if you have one, sorry, this is a rough schematic diagram of an RLC series circuit. Now, let me draw the physical component. Say inside this we are having a physical resistor. Here inside this box we are having a physical inductor, and inside this box we are having a capacitor. Now, it doesn't matter that whether you physically place them this L below this R and then this C, or it is like whether L is here, like you are having L here and then you are connecting them like this. It is still having the same schematic diagram, or else you can do any sort of manipulation to them, but the topology, that how RLC they are connected, will remain same. However, if you want to change the topology, what you should do, like instead of having a series connected RLC, you can do what? You can just let me draw it. Instead of having L, you connect it here. Now you will have a circuit with different topology. Now that makes sense that topology is a branch of mathematics where mathematicians do not concern about how things are connected, rather they are concerned that means who is connected to whom and how they are connected. Like it is one interconnection is sufficient. Now what is the like if you try to conceive that between two, actually from where all this the idea of topology come, it was due to Leonhard Euler. First he started this problem, although we do not mention this name here in topology because his problem which he started, we consider it as the first stepping stone for our discussion on graph theory. It was means one mayor of one city asked him to solve a problem. It was famously known as Keynesburg bridge problem, where Euler has to find out, or rather Euler had to find out that how to connect two means two sides or two banks of river, probably river, or it was a large lake. I cannot recall it at this moment, but at that Keynesburg he has to find out a path that can means one can execute a to and fro journey, and there was odd number of bridges. So what he establishes that it doesn't matter what is the length of that bridge, but what does matter really, that whether these two are connected or not. So that was the first concept of topology. Then uh, in 18th and 19th there was some contribution from Riemann and Beta, and then after that there is Waker, whom we consider as the father of topology. So instead of going to that history of topology and much on its genesis, let us go to a mathematical description of topology, and I will try my best to keep it as simple as like uh, as close to our practical life as possible, because our purpose is not to learn abstract algebra, rather our purpose is to learn or to gain the working knowledge so that we can solve our control system engineering problem. So first of all we need to find out the definition of topology. There is certain problem in my end. Just a minute. Oh God. So here we want to define first what is topology. So topology is, let us consider, let us have a set now. A collection of subsets of capital X, tau, a collection of subsets of capital X, is said to be a topology on X if one X, and we will denote null set by this symbol phi. X and means empty set phi belong to tau. Then the arbitrary union of any finite or arbitrary union of the members of tau is in tau. Third point is, give me a minute. And the intersection of any two sorry, here one thing you please note, it is not infinite, rather finite intersection of any two members of tau is in tau. Like algebra, it is an axiomatic subject. Like we first define axiom and then we try to find whether a given structure or a given set is complying with that axiom or not. And if it is, then it is a topology. If it is not, then it's not a topology. So these three conditions, if let me clearly explain once again. So the finite intersection of any two elements of tau is in tau, and if any means set together with its subset comply with these three requirements, let me clearly tell you. We have a non-empty set X. Obviously it need to be non-empty because its subsets will form a collection like all the subsets. Here we are not mentioning whether the subsets are proper or improper. Do remember that the whole set is a subset of its own. So when we are talking about tau, it contains a collection of such subsets of X. But here also one thing I would like to mention, that it never claims that tau has to contain all the subsets. But tau must contain the subsets in such a way that the first condition X and psi, X and phi, that is the null means empty set, and the main set belong to tau. The arbitrary union of the members of tau is in tau. The finite number of intersections of any members, finite intersection of any members of tau is in tau. So if these three conditions subset collection satisfies, then we call this ordered pair the ordered pair is a topological space, right? This ordered pair is known as a topological space. Now we will consider a few examples. So examples, let us take a few examples. Let us have, and do remember, as I have mentioned, that there is no such guarantee that tau will contain all the subset of a set. Obviously, it is easy to understand that we can have different topology for a single set. So instead of literally describing those things, let me take a set that contains, the cardinality of that set is 6. 6 elements are there. Now let us consider our topology tau 1. Now by virtue of the definition, X and phi must be in that, must be present there in tau 1. In addition, there is A, there is C comma D, there is A comma C comma E, there is B comma C comma D, right? So here, see, first of all, it satisfies condition 1 as X and phi are there. Now there are means subsets, all these are subsets, last 4 elements are subsets. Now here you can see that their intersection and their union, whether their union belongs to that or not. Sorry, here I have made a mistake. It is so their union is still in X tau or not. So what you will get by taking union of A, C, D. Okay, so I make a little change here instead of means just a minute. B, C, D means B, C, E, A. I make it B, C, D, E, A. So what is the issue here, that if you take intersection union of any two like phi and A, it is still in A, X and CD, that is X, still in tau, then A and CD, if you take union, that is ACD in here. Now if you take union of this or this or these two, you will get the whole set X, and that is present in this tau 1. So this is an example of topology. We can say that x comma tau 1 is a topological space. Now let us try to understand what or when we can't call it anymore a topology. Let us consider another collection of subset tau 2 for means let us include the two members x and phi, because if we discard them, then there is no meaning of considering or means proceeding further with the structure tau 2. We have here A, then C comma D, then A comma C comma E, and comma B C D, right? So here one thing you can see, that if we take union of C comma D with A comma C comma E, the set will be getting, that is A C D E, which is not a member, or which therefore tau 2 is not a topological space with X. Right. Let us consider, so here union failed. Now let us consider another tau 3 with that same set, then now see, if we obtain the intersection of these two, now C comma F is not in this tau 3, this collection tau 3. So tau 3 is not a topological space. Well, now Here, when I mention, you have noticed that I have mentioned that it is like we are considering finite number of intersection. So why this finite intersection is important? Let me discuss. Like so, what we can discuss that let X be a non-empty set and let tau sorry and let tau be the collection of all subsets of X, then tau is called the discrete topology on the set X, and correspondingly the topological space X comma tau is a discrete topological space, right? So here it is a discrete topological space. Now let us consider that obviously one question comes in our mind, then what is indiscrete topological space that let X be any non-empty set and tau only contains, then is called the indiscrete topology and X comma tau is called the indiscrete topological space. So here what we can propose that that let x comma tau be a topological space and every singleton means one element, having only one element, subset of x is in tau, then tau is necessarily a discrete topology. Right. Now, in this context, let us define the notion of open set and closed set. Actually, more formally it was open interval and closed interval, but in this topological discussion, we inherit it and make it open set and closed set. Let x comma tau be any topological space then the members of tau are said to be open sets. Now here one thing you must notice that a same set can be open set as well as closed set, unlike an interval, that is if it is open then it cannot be closed, and if it is closed it cannot be open. A set at the same time it can be open or closed or both, or maybe it is not open not closed, right? We will give you some example. Now let us write one proposition that if x comma tau is a topological space such that x and phi are open set, any arbitrary union of open set is an open set any finite number of intersection of open set is an open set. So please note that I have mentioned this word, any finite number. What is the implication or rather importance of this finite number here? Do we think that infinite intersection of open set are not open? So what I am trying to claim, infinite number of sections of open sets may not be open. While finite numbers are always open, infinite number may not be open. Let us consider n be the set of all positive integers, right? Now let us consider the topology tau consists of the empty set phi and each subset S of n in a way that complement of S in n, that complement of S in n, sometimes we denote it by is a finite set, then tau is a topology on n. So here now you can easily verify that tau, the collection, it satisfies all, like and S can be in, the whole n can also be a subset of n, and your tau contains n and phi and the other subset in such a way that their complement in n is a finite set, then tau is a topology on n. So obviously you can find out the complement of each set. Now here one thing, I am just taking this example to make you understand that like why I have been mentioning that it is a finite intersection. We can select is like it is a set that we conceive like this. So here one thing is very clear that we can write this set where is a natural number. The n belongs to n. Simple thing. So obviously you can find it out that for such collection, obviously the like complementary set, whatever you take, will be means finite. So it is each Sn, or better to say it is Sn. Like we can have S1, S2, S3 when we or where we will replace this small n by suitable integer. Sorry, suitable natural number. Now here it is easy to understand that each of our Sn is an open set in that topology tau, since they are complements are finite. Now, if you take the intersection, then what is your guess about this intersection? What we will get? Any idea? Let us look at this expression. So by looking at this, you can see that 1 is common and it is irrespective of the choice of your natural number. 1 is an element of all the set you are going to generate. So obviously you are going to get here 1. Now the problem with this 1 is very funny, that if you take the complement of 1, obviously you will get a set that is a set of all natural numbers excluding 1. So that is not n. Or however, the number of members present in the set is not a finite set. Therefore, 1 is not open, and that is why we will discuss more on this, means typical topology in our upcoming discussion when we will discuss closed finite topology. However, here one thing that is very important to note, that why we are always means I vouch for finite number of intersections rather than infinite intersections, right? So if you go for infinite intersection of open set, you may end up having a set that is not open, right? And now when we are discussing on open set, we must know the notion of closed set. What is a closed set? Closed set, just like the definition of open set, we can define closed set. So what is closed set? The definition of closed set is, let x comma tau be a topological space a subset S of X is said to be a closed set in that space, topological space x comma tau, if its complement in x is like means x by s, sorry, not this, yeah, is open in that same space x comma tau, right? So if we take that example of set x is equal to a comma b comma c comma d comma e comma f, and we are having tau is equal to, what was tau, that x comma phi comma, just a minute, let me just check where I have written that expression of tau. Yeah, it is x comma phi comma a comma c comma d comma a comma c comma d comma right. This was our tau. Now what sets are x, phi, b, c, d, e, f, a, b, e, f. Please pay your attention because this is very important. Then B, E, F and A. These are the few examples of closed set. Now obviously you can notice that here these A, B, E, F and B, E, F, they are not the member of the topological space tau. However, if you look at the definition, it is written that x comma tau be a topological space, a subset S of x is said to be a closed set in x comma tau if its complement is complement in x is open. Like if it is not required that the subset which you are going to claim or which we are going to assess for its closeness, it's belong to tau or not. It is important to check whether its complement belong to tau or not. So that is why it is very important to check. Now see whatever set I have written here. So x complement is phi. Phi belongs to your set tau. So phi is an open set. So it is so phi and x you can understand. Now let us take this one, B, C, D, E, F. So what is their what is their complement? Their complement is A and that is open, so it is closed. And by similar argument, S complement B, C, D, E, F is open and that is why A is closed. Now here the other two members which are not actually present in our existing topology tau, A, B, E, F. Now if you drop A, B, E, F, what you will find that C comma D you will be getting, and C comma D is open. So ABEF, the set, although it is not being a member of tau, it is still, we will consider it is closed over the topological space x comma tau. And the same type of argument, if you take BEF, you will be having that complement ACD that is present in tau and open. So it is an closed set. Now I would like to give you some more example. Please note that this open and closeness of set, that is means do not get confused with them, because the name open set or sometimes becomes closed set. Like as I have mentioned, the set A, that is open as well as it is closed. The set B comma C comma D comma E comma F, they are open and closed. Now if you consider another set, like any subset we can pick. Now let us consider a set B comma C. So what about B comma C? Whether B comma C is open or B comma C is closed. Now for openness, what we need to check, let us get back to that definition of open set. This notion of open set is very important, so please pay your attention. X and phi, any arbitrary union of open set is an open set. Any finite number of intersection of this is an open set. So basically, let us check whether it is an open set or not. So if we take B comma C and we and also that it has to be a member of tau. That open set has to be a member of tau. So when it is not a member of tau, you cannot claim it as an open set, right? So B comma C is not an open set. And also, if you try to verify the closeness of B comma C, then what you will see that closeness B comma C's complement is like ADEF, which is not present in tau. So it is also failing to comply with the definition of closeness. So B comma C is a subset of X which is neither open nor closed. Such a funny thing. Now we can take C comma D. The set C comma D says C comma D belongs to tau. So C comma D is open, right? Because if you take that C comma D is fulfilling the condition, so C comma D is open. However, if you take the complement of C comma D, then you will be having what? You will be having ABEF. ABEF is not open in tau, right? ABEF is not open in tau. ABEF is not there in tau. So C comma D is open but not closed. So you may find it quite may give you some kind of satisfaction that at least the first time you are getting someone who is not trying to confuse you. C comma D is someone who is very gentleman. He claimed that, boss, I am the open set but I am not closed. And this one B comma C is an you can say it's an unsocial person. He said, I do not want to belong to anything, means neither open nor closed. Now if you consider A comma B comma E comma F, this is closed. Obviously this is closed, we have verified. Now whether it belongs to tau? No. So this is not open. So we can say that So these two are gentlemen. They are C comma D is open set but not closed, and this is closed but not open, and A and also X and phi and this set B C D comma E comma F, all these four are totally hypocrite. They are neither open nor closed. Means sorry, they are both open and both they are closed as well as they are open. So it is difficult for you to tag them in any category, or you can tag them in both the category you have. Now what we can say that would like to have a proposition. Just a minute. So let us write a proposition related to closed set. Let x comma tau be a topological space then phi and x are closed sets. The intersection of any, better to write the arbitrary intersection of the closed sets is a closed set the union of any finite number of closed set is a closed set. So it is very clear that the second and third point is just a complement of what we have studied there in for open set. Like second point for open set, it was the arbitrary union of open sets were open set, and the third point of for open set was the finite number of intersection, and we have discussed that if the number of intersection is infinite, then if you have you are taking intersection of open set, you may end up with having a closed set. So that is the case here. Let us you can prove it, and if you cannot prove it, then you please let me know, because I intentionally drop all this proof from our course of discussion. Rather, I am trying to discuss more and more examples so you could easily relate. We are again I am trying to mention that although I am discussing topics from advanced mathematics, but it is not my goal to train you to become a mathematician. Even I am not a mathematician, and I never had a course in math major and math minor. So you can always understand that I am not an Indian mathematician nor a physicist. So I have a very small idea about mathematics, but what I want that to give you or to impart the bare minimum knowledge in you, so with that you can easily understand any standard automatic control paper either published in IEEE Transaction on Automatic Control or in Automatica or in any standard publication, and you must be acquainted with the tools. Like you need not to know the craftsmanship of the tool. Like mathematicians are the person who are working on the craftsmanship. Like how, if you consider a hammer, a craftsman is someone who is trying to advance the design of that hammer. We are not that. We are just someone who need to know that how to means utilize a hammer for means nailing wooden structure. So that is what is required here. So with this, I would like to stop today's discussion.